ready to go, guys. Chris from G Research is just going to speak about G Research. Thank you very much for
perfect. Hello. Yeah, just a very quick one from me. Thank you very much for coming tonight. I'm part of the talent acquisition team at G Research. It was just to tell you a little bit about what we did. I know it's quite secretive, or there's not really much information out there about what we actually do. Basically, we are a quantitative research and technology firm, which meant absolutely nothing to me when I first heard that, but I nodded through the interview and said I understood. What it basically means is we take huge data sets, we analyse them, and we hopefully discover the secrets of the stock exchanges that we then pass that information on to our clients to trade on. The fun part is that that's really, really difficult to do. You need two things. You need really smart people, and you need really good technology. So in G Research, we've got about 850 staff now. Well, we've got about 850 staff now. Some of the smartest mathematicians in the world. We hire from sort of all over the world and try and find the best. We've got about 400 engineers now as well, and they've built an amazing platform. You get to work on really, really hard problems, you get to work with really smart people, and you get to do it in a really fun place. So if anyone is interested in finding out a bit more, I'll be about later on tonight. Feel free to grab me for a chat. Thank you.
Somebody does. Well, I mean, it's some freelance work, but cool.
All right, so I'm going to start my timer. As Michael mentioned, I've got like 2 hours. Hopefully I won't get close to that, but you guys are welcome to interrupt and ask questions. So I've given a couple of talks about Miniscript, usually in like 20 or 30 minute time slots, where basically I try to give a high level overview of what this project is, and why you should use it, and why it makes Bitcoin script accessible in ways that it hasn't been. In particular, you can do all sorts of cool things that in principle Bitcoin script can do, but in practice you cannot, for various just like algorithmic practical reasons. Bitcoin script is just not easy to reason about, it's not easy to develop with, it's kind of, not fragile, but it's got a lot of sharp edges, sort of the opposite of fragile. You'll feel very fragile trying to use Bitcoin script. But since I've got a whole pile of time and a reasonably technical audience, I'm going to try to do something different here. I'm going to talk in a fair bit of detail about some of the issues with Bitcoin script and some of the motivation for Miniscript. And then I'm going to try to build up some of the detailed design of Miniscript, which is essentially a reinterpretation of a subset of Bitcoin script that is structured in a way that lets you do all sorts of analysis. I'm going to try to build up the design, and I'm going to talk about some of the open problems with Miniscript. And there's maybe kind of an irony here that there are so many difficult things with Miniscript, given how much simpler it is than script. This sort of highlights how impossible it is to work with script to begin with. That even after all of this work we put into structuring things and getting all sorts of nice, easy algorithms, there are still a lot of natural things to do that are quite difficult, in particular around dealing with fee estimation and with malleability. So let's get started. So first, I'm going to spend a few slides just giving an overview of what Bitcoin script is and how it's structured. As many of you probably know, Bitcoin has a scripting system that allows you to express complicated predicates. You can have coins controlled not only by single keys, but by multiple keys. You can have like multi-signatures, threshold signatures, hash preimage type things. You can have time locks. This is how Lightning HTLCs are created. You can do weird things like have bounties for finding hash collisions. Peter Todd put a few of these up, I think in 2013. There's a whole bunch of Bitcoins you can take if you find a hash collision. The one for SHA-1 has been taken, but there are ones up for the other Bitcoin hashes for SHA-2 and the combo hashes that you can still take if you can find a collision. And the way you can do this is with this thing called Bitcoin script. And Bitcoin script is a stack-based opcode. It's basically a stack-based assembly language. It's very similar to Forth. If any of you are 70 years old, you might have used Forth before. It's a very primitive, very frustrating language, and Bitcoin sort of took like a bunch of the specific frustrating parts of it and not the rest. A quick overview. Every Bitcoin script opcode is a single byte. There are 256 of them. They are allocated as follows. You have 78 for pushing data of arbitrary size. All your stack elements are these sort of byte vectors. So the first 76 opcodes are just like push this many bytes into the stack. Then there are a couple more general ones. We also have a bunch of special case opcodes for pushing small numbers. In particular, -1 through 16 have their own opcodes. Then for future extensibility, we have a bunch of no-ops. And then for historical reasons, we have 75 opcodes that are synonyms for what we call op return, just fail the script immediately. For even sillier historical reason, we have 17 opcodes that will fail your script even if you don't execute them. You can have like if branches that aren't accessed, but if there are certain opcodes in there, it will fail your script. And that's probably was a historical mistake in the Bitcoin Core script interpreter that we can trace back, I guess, to 2010 through 2012 is when most of this came to be. And then finally we have 57, what I say, real opcodes. And these are actually the core of Bitcoin script. So of these real opcodes, we have a lot of things you might expect. We have the 4 control flow ops. Those are if, else, else if. And then we also have a not if, which will save you a byte in some cases. Basically, it's the same as if, except it will execute if you pass it a 0 rather than executing it if you pass it a non-zero. We have a few oddball opcodes. Let me quickly cover those. We have opverify, which will interpret its data as a Boolean. If it's true, then it passes, that's great. If it's false, it fails the script. If dup, if you pass it a true, it will duplicate it. If you pass it a false, it will just eat it. We have depth and size. Those are interesting. Depth will tell you the current number of elements in the stack. Size will tell you the number of bytes in the most recent element. These are interesting, I'll explain in the next slide, mainly because they make analysis very difficult. Because they suddenly put a lot of, they put constraints on aspects of your stack that otherwise would not be constrained. So when you're trying to do general purpose script analysis, these opcodes will get you in trouble. We have opcode separator, it's just weird. It was there originally to enable a form of delegation, where after the fact you could decide on a different public key that you wanted to allow spending with, but that never worked. So code separator does a very technical thing of unclear utility. We have 15 stack manipulation opcodes. These basically rearrange things on your stack. You've got a bunch of items. There are a whole bunch of things that will just like reorder these or duplicate certain ones of them or duplicate certain combination of them or swap them and all sorts of crazy stuff like that. We also have a couple of alt stack opcodes. We have one that will move the top stack element to the alternate stack, one that will bring stuff back. So those of you who are familiar with the charlatan Craig Wright may be aware that you can design a Turing machine using two stack finite state automaton or something like that. It's plausible that the alternative stack in Bitcoin was inspired by this, but actually this provides you no expressive power. It's just the only things you can do with the alt stack in Bitcoin are move things onto it, move things off of it. So sometimes this lets you do things and it just manipulate the stack in a slightly more efficient way. But all it is a staging ground. You can't do computations there, you can't manipulate the alt stack directly, you can't do anything fun. We have, looks like 6 different opcodes that compare equality. I'll talk a bit about those in the next slide. The reason there are 6 of them is to make analysis hard. We have 16 numerical opcodes. These do things like addition, subtraction, Boolean comparisons, which is kind of weird. There's special purpose opcodes for incrementing, for decrementing. There used to be opcodes for multiplication and division and concatenation and a bunch of other stuff. Those have turned into the fail even if not executed opcodes. Those are disabled many years ago, and the way that they were disabled caused them to have this weird failing behavior. Then we have the 5 hashes in Bitcoin, which are RipeMD 150, SHA-1, SHA-2, and then there's various combinations of these. There's hash 256, which means do SHA-2 twice. There's hash 160, which means do SHA-2 and then RipeMD 160. And then finally we have the checksig opcodes, which are probably the most well-known and most important ones, and also the most complicated ones. We have checksig, which checks a single signature on the transaction. We have check multisig, which checks potentially many signatures on the current transaction. Okay, so some miscellaneous information about script, some of which I've hinted at. We have a whole pile of limits, which I'll talk about in a sec. Stack elements are just raw byte strings. Okay, there's no typing here, there's nothing interesting, they're just byte strings that you can create in various ways. The maximum size is 520 bytes. This is the limit set by Satoshi. think because you can put a 4,000-bit RSA key into 520 bytes. Bitcoin does not and never has supported RSA keys, but Satoshi did take a lot of things from the OpenSSL API, and we think this might have been one of them. That's fine. There's no, as far as I'm aware, there's no use for stack elements that are larger even than 60. I guess with DER signatures, they're larger than like maybe 75 bytes, but you can go up to 520. There are many interpretations of these raw byte strings, though. I said we have no types, but actually every opcode sort of has kind of a notion of typiness in it. A lot of the hash ops and stack manipulation things just treat them as raw byte string. That's great. But all the numeric opcodes treat their things as numbers. In Bitcoin, this means specifically up to 32-bit signed magnitude numbers. Signed magnitude means the top bit. If it's 1, you have a negative number. If it's 0, you have a positive number. This means you have 0 and negative 0, for example. Those are two distinct things. You also have a whole bunch of non-canonical encodings. You can put a bunch of 0 padding into all your numbers, and those will continue to be valid. But if you exceed 4 bytes, then that is not a number. So for example, you can add sufficiently large numbers, and you will get something that's too big, and so it's no longer a number. So if you keep using op-add and you're not careful about it, then you might overflow, and then the next op-add is going to fail your script. So if you're trying to reason about script, you need to know these exact rules. Some things, the if statements, op-verify, a few others, but oddly not the Boolean and or, will interpret these things as Booleans. Booleans are similar to numbers. If you encode 0 or negative 0, that counts as false. If you encode anything else, that's considered true. The difference between Booleans and numbers is that Booleans can be arbitrarily sized. Okay? So you can make a negative 0 that's like 1,000 bytes long. This will not be interpreted as 0 by any of the numeric opcodes. They will fail your script, but they will be interpreted as false by the Booleans. Okay? Something to be aware of. If you're trying to reason about script, you need to know these rules. And then finally we have the check sig and check multisig, and those are the closest to doing something sane. They interpret their arguments as public keys or signatures. The public key is actually now, okay, that's not consensus, but the public keys are supposed to be well-formed. The signatures are supposed to be either well-formed or like the empty string, which is how you indicate no signature. These are not consensus rules. You can actually put whatever garbage you want in there, and the opcode will simply fail. This is a comparison to C. If any of you guys have done a lot of C programming and tried to reason about it, or tried to convince the C compiler to reason about your code instead of doing insane and wrong things, you may notice that the literal 0, if you type that into your C source code, that is a valid value for literally every single built-in type. 0 is an integer of all sizes, 0 is a floating point, 0 is a pointer to any arbitrary object, 0 is an enum, 0 is everything, and there's no way to tell the compiler not to interpret 0 that way. And of course the C standard library and POSIX and everything else uses a constant 0 as an error return code about 40% of the time, so you need to deal with this fact. And this infuriating aspect of C was carried over to Bitcoin script in the form of the empty string being a valid instance of every single different way of interpreting script opcodes. Okay? So that's just the script semantics. Those are a bunch of weird edge cases and difficulties in reasoning about the script semantics and trying to convince yourself that a given arbitrary script is doing what you expect. Additionally, there are a whole pile of independent and kind of arbitrary limits in Bitcoin script. As I mentioned, stack elements can only be 520 bytes. Your total script size can only be 10,000 bytes. You can only have 201 non-push opcodes. A non-push opcode is something a little bit weird. A push opcode includes all of the things you expect to be pushes, like pushing arbitrary data onto the stack, pushing a number onto the stack. It also includes a couple opcodes that are not pushes, but they sort of got caught in a range check, just comparing the byte values, so you need to know which ones those are. And also in check multisig. So this 201 opcode limit actually only applies to the whole script regardless of what gets executed. So you can have like all sorts of if branches and you just count up all the opcodes. Except, if you execute a check multisig, then all of the pub keys in that check multisig count as non-push opcodes, even though they're pushes, but only if they're executed. Okay, so there's a very technical rule that is, I think, maximally difficult to verify, that, as far as I know, nobody was aware of until we did this Miniscript development, and we found this lurking in the Satoshi script interpreter And you're like, oh, okay, so. In our Miniscript compiler, we have to consider that. That's a resource limit we hit sometimes in trying to work with Miniscript. As a SIGOP limit, this is something a lot of you are familiar with. This is what restricts your ability to do enormous check multisigs and other interesting things. There are a couple different SIGOP limits. I think the only consensus one is the one that limits like given block to have 80,000 SIGOPs in it. And then there are policy limits for how many SIGOPs you can have in a given transaction. And these are, I think, different for raw script and for P2SH and for SIGWit. Also, there are 1,000 elements. You're only allowed to have 1,000 elements on the stack. It's basically impossible to get 1,000 elements on the stack. This limit doesn't really matter, but just to make sure that your optimization is constrained in as many dimensions as possible. That's an additional thing. So for what it's worth, in BIP 342, which is TapScript, we fixed a whole pile of these. In particular because having so many independent limits was making a lot of our Miniscript work more difficult. So we cleaned this whole mess up. We kept the 1,000 element stack limit because it provides some useful denial of service protection, and it's so far away from anything we know how to hit without doing really contrived stuff. But we, like, for example, combine, I think we got rid of the script size limit because there are already limits on transactions and on blocks, which are great. We kept the stack element size limit just because that's not doing anything. All of our stack elements are limited in practice anyway. But then we combined the opcode limit and the SIGOP limit. We got rid of check multisig. And so now that's a single, sort of the most difficult thing to keep in mind when you're constraining your scripts is now a single one-dimensional thing. So now, absent really extreme things that you might be doing that are all outside the scope of Miniscript, you actually just have a one-dimensional limit. So if you're trying to work within these limits, it's much easier in TapScript, which will be in SegWit v1. I hope, knock on wood. A couple particular opcodes that I hate. Everyone else I work with has a different set of opcodes. Everyone who works with script has their own set of opcodes. These are the ones that I hate, okay? So pick and roll, first of all. What these opcodes do, they take a number from the top of the stack. One of them will copy that many elements back to the top. The other will move that many elements back to the top. So now you are taking one of these arbitrarily typed objects, who knows where you got it, and now you're interpreting it as an index into your stack. So if you're trying to reason about things, now you have stack indices as a new kind of thing that is happening in your script. And so when you're trying to constrain what possible things might happen, that's a whole nother dimension rolled up in there. Numerics overflowing, I mentioned. The check multisig business, I mentioned. Depth and size, I mentioned. I mean, these are simple opcodes, but they're just extra things to think about, right? If you're trying to reason about what the script interpreter is doing, it would be nice if as many of the internals of that interpreter you could just take for granted and that weren't available for introspection to users, but they are. These opcodes make those available for introspection, so now they're mixed in with your reasoning about what values might be possible. An if-dup does a similar annoying thing. Below, of course, you can use just opt-up and opt-if together to get an if-dup, but this opcode just happens to be the only one that will conditionally change the depth of your stack, depending on whether what you give it is considered true or false. So when you're trying to keep track of your stack depth, when you're reasoning about scripts, it gets in your way.
So some of these, what are these useful? Are they
where are these useful? So actually, we use ifdup in Miniscript quite a bit. Oh, do I have an internet connection on this computer? Do you know?
Yes.
Maybe. So later in the talk, I might go to the Miniscript website, which has some detailed justification for some of these things. So ifdep gets used in Miniscript. None of these other things are useful for Miniscript. But let me give a couple justifications. So pick and roll, I have used before, well, only in demonstrations of weird script things, I guess. But I can imagine cases where you want to use pick and roll to manipulate your stack. If you have a whole bunch of stack elements in a row, and say you're trying to verify a signature that's really deep in your stack, then you can use oppick to bring that public key and signature to the top of your stack, verify them, and then move on with your life without trying to swap them out a whole bunch of times. Op depth and op size do actually have a bunch of uses. Op depth is kind of cool. We use this in Liquid as a way of distinguishing between two multisig branches. So we have the standard 11 of 15 functionary quorum check, and we also have a 2 of 3 emergency withdrawal check. And you're allowed to use either one of these, and the emergency withdrawal has a time lock on it. And this is how liquid coins are protected. So we're using opdepth to count the number of signatures provided. And if you give the script 11 signatures, it knows, oh, this is a functionary signature, let's use that branch. If you only give it 2 signatures, it knows to use the other branch. So there's an example of what opdepth is for. Opsize has a bunch of cool applications. One is, if you use opsize on an ECDSA signature to constrain the size to be very small, this forces the user to use a specific nonce that is known to have a bunch of 0 bytes in it, that has a known discrete log, which is the multiplicative inverse of 2 in your secret key field. And then that means that by signing in such a way, by producing a small enough signature, you are revealing your secret key by some algebraic solving. So you can use opsize to force revelation of a secret key. You can use opsize to very efficiently force a value to be either 0 or 1 through a cool trick we discovered in developing Miniscript. You use opsize and then op equal verify in a row. That will pass 0 or 1, but it will fail your script otherwise. Because the size of 0 is 0, it's the empty string, and the size of 1 is 1, but no other value is equal to its own size. And so the equal verify will abort. So in an early iteration of Miniscript, before we realized that we had to depend on a lot of policy rules for non-malleability, we were using size equal verify before every one of our if statements. Because otherwise, a third party could change one of our trues from 1 to some arbitrary large true value, change the size of our witnesses, and then wreck our fee rate. We don't do that now because we had to change strategies because there are other places where we had similar malleability, and ultimately we weren't able to efficiently deal with it in script. But if you really want like consensus guaranteed non-malleability, not like policy minimal if guaranteed non-malleability, opsize is your friend. You're going to use that a lot. Oh, and one more thing. Opsize is for.
Are using Lightning scripts.
Yes, exactly. As Ariard says. Sorry, and I shouldn't say names while I'm on camera. In Lightning and in other atomic swap protocols, you want your hash primitives to be constrained to 32 bytes. The reason being, this is kind of a footgun reason. Basically, if you are interoperating with other blockchains, or you want to interop with like future versions of Bitcoin or whatever, a concern is that maybe Bitcoin allows hash primitives that, well, it will allow anything up to 520 bytes on your stack. But if you're trying to interoperate with another system that doesn't have such a limit, say like whatever your offline Lightning implementation protocol is, maybe some bad guy creates a hash primage that is larger than 520 bytes. It passes all the offline checks, but then you try to use it on the blockchain and you get rejected because you're just not, it's just rejected because it's too large. Similarly, if you're trying to do a cross-chain atomic swap and one of the chains has a different limit than the other, then you can do the same thing. You can create a hash primage that works on one chain but doesn't work on the other, and so now you can break the atomic swap protocol. So you want to constrain your hash primitives to being 32 bytes. Because everybody supports 32 byte primitives. That's enough entropy that you're safe for whatever entropy requirements you have. And opsize is the way that you enforce this. And we'll see this later if I can get to the Miniscript site and when we look at some specific fragments. We have like a 32 opsize, 32 equal verify, like confirming that we have 32 byte things.
I'm assuming if it had no use, you could disable it.
Right, yeah. So the only thing here, which we disabled in TapScript, is check multisig, ironically. And that sounds like the most useful, but it's actually, in some sense, has the worst complexity to value ratio. There are other ways to get what check multisig gives you that doesn't have the kind of limitations and that doesn't have the inefficiency of validation that check multisig does, and I think I'll get into that in a bit later on. So are there any more questions about this slide? I have one more slide of whining about script, and then I'll get into the real talk. Look at that, I've already spent 20 minutes just complaining about script. I'm sorry for boring you guys, but this helps me. Right. Another random list of complaints about scripts and surprising things. As I mentioned, boolean and boolor, despite having bool in the name, do not take booleans, they take numbers. If you put something larger than 4 bytes into these opcodes, they will fail your script. Peter Willett claimed that he didn't know this until I pointed it out to him. Okay, so I mean, everyone, no matter how long you've been doing this, you get burned by like just weird, surprising stuff like this. Except, so I've been saying numbers are maximum 4 bytes. Actually, check sequence verify and check lock time verify have their own distinct numeric type that can be up to 5 bytes because 32-bit signed magnitude numbers can only go up to 2 to the 31, which doesn't cover very many dates. I think those run out in 2038, as many of us know for other reasons. So in order to get some more range, we had to allow an extra bit, which meant allowing an extra byte. So these values can actually be larger than any other number. So they're actually there's actually 2 distinct numeric types as well as a Boolean. I mentioned the checked multisig opcode counting weirdness. And then one thing that burns you if you don't, basically if you don't unit test your stuff, but no other way, is the numeric values of the push number opcodes are really weird. It's hex 50, plus whatever value you're doing, -1 through 16, except 0. 0 is not 0x50. If you use 0x50, it'll fail your script. 0 is 0x00. So you need a special case 0. If you're naively thinking you can just take your number and add decimal 80 hex 50 to it, like you might say if you were trying to support SegWit and you have in the wild the only version number being used being 0, but every other version number having this 0x50 added to it. This is a very easy mistake to make that you actually wouldn't notice with real world data. But there we go, that's life. Yeah, 0 is 0. Everything else is what you expect plus 50.
What opcode is 50?
50 is op reserved. I think it was always called op reserved. Unlike a lot of the other reserved opcodes that didn't used to have a name and then we had to disable it because it triggered undefined behavior. I think op reserved has always been reserved. And I think it's always been because you would expect 0 to go there. And if you weren't going to put 0 where it should be, then the safest thing to put there would be fail the script. Right?
What is the purpose of 050 element NX in SegWit version 1 that you are putting into the witness stack? Well, it is allowed to put it.
So in SegWit, your witness programs have a numeric opcode, a numeric push indicating your version number, followed by your actual 32-byte program.
No, I mean in the taproot already. In the taproot, you can have in the witness after the signatures the byte 50. That is some annex or something. There is a description like you shouldn't use it. It is like for future use. So what future use you are planning on that?
If you can try and repeat the question.
Yeah, sure. So the question is about the annex field in SegWit v1 taproot or TapScript signatures. Let me see if I can remember the justification. So this is a.
You may have like a pair input lock time instead of using the end sequence for lock time.
That's one application. Let me just give like a general answer because I'm kind of I'm forgetting how exactly it works. The idea is the annex is covered by the signature. So the idea is you can add arbitrary extra data that will be covered by the signature. And this in some future versions, like somehow something lock time related, this could be useful for like adding new opcodes that would conditionally constrain your signatures in some way. But as of now, there is no use for it. So it's basically this extra field that gets covered by the signature and that may in future do something interesting for other future opcodes that don't exist yet. And we're just putting it in there now so that we won't require a hard fork to do it later. But right now it is constrained by policy to always just be empty because there's no value then. Yeah, and I wonder if the number 0x50 is used there.
Yeah, 050.
I think that might just be a coincidence. Maybe not. It doesn't sound like a coincidence, does it?
It's to avoid like some weird collision with SegWit version number or something like this.
Yeah. Oh, yeah. It's not a coincidence, but the exact means of where the collision was imagined to be, I don't remember.
It's in the footnotes of the paper.
Yeah. Yeah, I'd have to read the pip to remember. Yeah. So I mean, as far as the general complaint about complexity, it's getting worse, but very slowly. But well, overall, it's getting better. I think there's a lot of crap that we really just cleared out with TapScript, and Taproot. But the annex is, I think, one place where you can still see this historic baggage carrying forward. Yeah. Okay. So, on a high level, let me just summarize my complaints about script, and then we're going to go into what Miniscript is and how Miniscript tries to solve these things. Okay. It's difficult to argue correctness because every single opcode has insane semantics. I talked about some of them. I didn't even talk about the bad ones. I just talked about the simple ones that are obviously crazy. It's difficult to argue security, meaning is there like some weird secret way you can satisfy a script? It's just hard. It's hard to reason about all the different ways, all the different script paths that might be possible. It's hard to argue malleability freeness. There are weird, surprising things, like you can often replace booleans with larger booleans, or you can replace numbers with non-canonical numbers. Stuff like this, which is forbidden by policy, so most of this class of attacks will be prevented on the network, but in theory, miners could try to execute something like this. And there are so many surprising corners, so many surprising ways in which things can be malleated that this is something difficult to reason about. Assuming you have a script that you're comfortable with from correctness and security perspective, it's difficult to estimate your satisfaction cost. It is if you've got like a script that can only be satisfied one way or a couple ways. You can just say, well, it's this many signatures and this many bytes. You manually count them up and then you put that in a bolt somewhere. But in general, if you're given an arbitrary script and you're trying to figure out what's the worst case satisfaction cost for this, like, this is very difficult to do. And the irony of this is that over in Ethereum land, they have the same problem, and this results in coins getting stuck all the time. And so as Bitcoin developers, this should be something that we can like kind of laugh at them for, because Bitcoin script is designed to be so that you can reason about it and you won't have this problem. But in fact, you do. We don't have Turing completeness, we don't have arbitrary loops, we don't have all these complicated things that make it intractable in Ethereum, but it's intractable anyway for no good reason. So, Miniscript, as we'll see, solves this. It's difficult to just determine how to work with an arbitrary script, okay? You don't know which signatures and hashes and time locks or whatever you might need to satisfy an arbitrary script. You basically can only support scripts that your software explicitly knows how to recognize by template matching or whatever. And then even if you do know what you need to satisfy the script, actually assembling it in the right order, putting all the signatures in the right place, and like putting the ones and zeros there to flip your booleans and all that kind of stuff, it also requires a bunch of ad hoc code. And fundamentally, the issue here is that there's a disconnect between the way the script works. You've got this stack machine with a bunch of weird opcodes that are mostly copied from forth, and then some of them mangled in various ways, and then some of them mangled in other ways. But the way that we reason about what script does is you're putting spending conditions on coins, right? You've got a coin, you want to say whoever has this key can spend it, or maybe 2 of these 3 people can spend it, or maybe it can be spent by revealing a hash preimage, or after a certain amount of time has gone by, there's some emergency key or something like this. And our job as developers for Bitcoin wallet software or Lightning software or whatever is to somehow translate this high-level user model into the low-level stack machine model. And along the way, like as soon as you stick your hand into the stack machine, it's going to just eat your hand, right? And hopefully you get more than half your work done because you've only got one more hand. And then you've got to convince someone else of that. Andrew thinks that was funny. And then you've got to convince the rest of the world that what you did is actually correct, right? It's just very difficult, and as a result, we have very few instances of creative script usage. The biggest one is Lightning, which has a tremendous amount of development power pointed at it. Much more than should be necessary just for the purpose of verifying that these scripts do what you expect. But nonetheless, that's what Lightning needs. Fortunately, it's what it has. But if you're just some loner trying to create your own system of similar script complexity to Lightning, you're going to be in a lot of trouble, okay? And actually one thing I did while working with Miniscript was looking for instances of people doing creative script things, and I found security issues in real life uses of script out there. And I don't even know how to track down the original people, and I'm not going to say any more detail about that. But the fact is this is difficult, there's not a lot of review, and the review is very hard for all of these reasons. Oh, I have a couple of fun, okay, I have 3 slides. 3 more slides of script whining. These are just a couple of fun questions, I'll be quick. So, here's a fun one. So we know that 0 and -0 can both be interpreted as false as booleans. Is it possible to create a signature that will pass that is 0 or -0? And this might be surprising. because we use the canonical value 0 to signal no signature. In cases like in check multisig, where you've got multiple signatures and you want to say like this key doesn't have a signature. But is it possible that you could check the signature, get false, but then actually it secretly is a valid signature? The answer is no for ECGSA, because the DER encoding requires that it start with the digit 2, which is not the start of 0 or -0, so we're safe by accident. With Schnorr signatures, you also cannot do 0 or -0. The reason being that in order to do so, you would have to set your nonce to be some R coordinate that is basically nothing but zeros and then maybe a 1 bit. And you can't, there's mathematically no way to do this. The Schnorr signature algorithm that we chose just doesn't allow you to do this without really breaking your hash function in ways that we assume are intractable. Another brain teaser, can you get a transaction hash onto the stack? The way you might want to for covenants, or the way that you might want to get something like opctv type behavior, just check template verify. That's Jeremy Rubin's kind of special purpose covenant thing. So you can actually do this, believe it or not, with ECGSA, but just it turns out not in a useful way. You can write a script that requires a signature of a specific form. So maybe one where your S value is all zeros and your R value is some specific point. And the public key is free. And the person satisfying the script is actually able to produce a public key that will validate given a specific transaction and that specific signature that's fixed in the script. And that public key, which you compute by basically running the ECDSA verification equation in reverse, is actually a hash run through a bunch of extra ECOPs. It's a hash of your transaction, it's a hash of what gets signed. So in theory, you could do like a really limited form of opctv just with this mechanism. It turns out you can't by accident because we don't have sighash no input. So every single sighash mode covers your previous out point, which in turn is a hash of your public key, which, or rather it's a hash of the signature that you're trying to match, which means that you cannot pre-compute this. And I apologize, I would need a whiteboard to really go through this. But basically there's an accidental design feature of Bitcoin that several layers deep prevents you from using this to get covenants in Bitcoin. And that is, I mean, that's the story of Bitcoin script. There's just always like really far-reaching remote interactions. And again, if you are trying to reason about Bitcoin script, you have to know this. Here's another fun one, which I hinted at earlier. What's the largest check multisig? What's the largest multi-signature you can do? I think check multisig with P2SH limits you to only putting 15 keys on, because there's a sig ops limit there. Check multisig with SegWit, I think limits you to 20 for other reasons that I don't quite remember. It turns out you don't need to use check multisig at all to do threshold signatures. You can just use check sig. You do check sig on a specific signature. If there's a signature, it will output 1, a valid signature. It will output 1, if there's not, it will output 0. You can take that 0, and you can just like move it out of the way, like onto the alt stack or something. Do another signature check. Then bring your 0, 1 back, and you just keep adding all these together. And so you can get a sum of all of your individual signature checks. And if that sum is greater than your threshold, which is easy to check with script, then you pass. That's exactly the equivalent, the semantics of check multisig, except it's actually a little bit more efficient for the verifier. So if you don't use that, then you are only limited by the amount of crap you can put on the stack based on the other limits. And you can wind up having multi-signatures that are 67? I think 67 is right. You can actually get 67 keys and 67 signatures onto your stack using this, which is kind of a cool way to bypass all these extra limits. And this is also the justification for removing check multisig in TypeScript, by the way. We have a new opcode, whose current name I forget, which basically does this all in one. Check sig add. Is that, oh nice, good. I'm glad. We had a bunch of weird extra letters there before. Check sig add. It does a signature check. Rather than outputting a 0 or 1, it takes that 0 or 1 and just adds it to an accumulator that's already in the right place. And so you can do this directly rather than needing like 3 or 4 extra opcodes. I think you need 2 opcodes, I think, per signature check. There you go, and then now you can eliminate all the weird complexity of reasoning about check multisig and using it. It's just much more straightforward. Okay, all right. On to Miniscript. So there we go. 40 minutes on why I hate script. And I will actually try not to use the full 2 hours, even though I have 2 hours of slides.
So last question on script. So
Yep.
it's very hard to it's very hard to judge Satoshi 10 years on. So I mean, there's a lot of subtle complexity here. Do you honestly think back in Satoshi's time, 2009, that you'd been able to have the perspective to design a better language?
Yep, so the question is, in 2009, could I have done better? Or could we expect Satoshi to have done better? Essentially, no. There are a couple minor things that I think could have been done better with a bit of forethought. But for some historical context, the original Bitcoin script was never used. It was a sort of idea for the smart contracting system, and then smart contracting was something that was in blog posts by Wei Dai or Nick Szabo and Hal and a few other people, just as some vague idea that you could have programmable money. And so script was created with the intention that you'd be able to do that. And so basically it was a copy of Forth. It actually had way more of the Forth language than we have today. We had all of the mathematical opcodes, then we had a bunch of other weird stuff. There was also this kind of half-baked idea for delegation, where the idea was that your script is a script you execute, but also, how about the witness is also a script to execute. And the way you verify is you just run both scripts in a row, and then if the result returns, if the final result is true, you're good. If the final result is false. And the idea is that your script pub key, which is committed to the coins, should check that the earlier script didn't do anything bad. Okay? And there were a couple of serious issues with these. Two that I'll highlight. One was there was an opcode called opversion, which would push the current, I see some grimaces, it would push the client version onto the stack. And so that meant that when you upgraded Bitcoin from, say, 0.1 to 0.2, that's a hard fork. Because now scripts that execute opver will push 0.1 onto the stack for some people and 0.2 onto the stack for other people. And you forked your chain. Fortunately, nobody ever used this opcode, which is good. Another issue was the original op return. Rather than failing a script like it does now, it would pass the script. And because we had this two-script execution model, you could stick an op return in what's called your script signature. It would run, and you wouldn't even get to the script pub key. It would just immediately pass. You could take any coins whatsoever, just by sticking an op return into your script sig. Bitcoin was launched in the beginning of 2009. This was reported by Art4s privately to Satoshi and Gavin in the summer of 2010. That was 18 months of you being able to take every single coin from Bitcoin. In a kind of sketchy commit, which overhauled that was labeled as being a makefile cleanup or something, Satoshi completely overhauled the script system. He did a couple of interesting things here. One was he fixed the op return bug. I think he got rid of opver a little bit earlier than that. Another was he added all the NOP opcodes. And around this time, if you guys are Bitcoin talk archivists, you'll notice that talk of soft forks and hard forks first appeared around this time. And it would appear forensically that around this script update, the one that fixed op return, was the first time that people really thought in terms of what changes will cause the network to fork. And before that, that wasn't even the way, nobody was really thinking of this as an attack vector, as an idea that different client versions might fork off each other, either explicitly or just because there's different script behavior. And so the NOP opcodes, all the no-ops were added as a way to add updates later in the form of a soft fork. And the fact that this happened at the same time as the op return fix is, I think, historically very interesting. I think it reflects kind of a big leap forward in our understanding of how to develop consensus systems. So knowing that historic context, the original question was in 2009, could we have done better? And the answer is no, basically. Our ideas about what script systems should look like and what blockchain should look like and what kind of, the difficulties of consensus systems, just nobody had any comprehension of this whatsoever. And the fact that there were bugs that let you steal all the coins for over a year tells you that nobody was even using this. No one was even experimenting. It was just really, it was just some weird, obscure thing that Satoshi had put in there based on some Nick Szabo blog posts, and nobody had really tried to see if it would fulfill that vision or not.
Did he did he literally copy something from Forth, or did he sort of reproduce it selectively or precisely from a manual? Or
So the question is, did he literally copy from Forth? Or did he use a man? So I don't believe there's any actual code copying from like any Forth compiler or something like that. The reason I say everything's copied from Forth is a couple specific things. Okay, all the specific things are the stack manipulation opcodes, like the swap and the to swap and op rotate, which rotates in a specific direction, which is not useful for Bitcoin, but is probably useful in Forth. All of the stack manipulation semantics seem to have come from Forth. These are just Forth opcodes, just reinterpreted in a Bitcoin context. Beyond that, I don't know Forth well enough to say. But there are a couple specific things that are really coincidental that suggest that he was using the Forth language as a blueprint.
right, because he either copied something or he made something up. But in the latter case, he must have thought about it.
The statement is either he copied something or made something up. And if he made something up, he must have thought about it. And I don't think that's true. I think he made up a lot of stuff without thinking about it.
They accidentally worked.
No, that's a very good point. Someone said it accidentally worked. And there are a lot of things in Bitcoin that accidentally work. That give you pretty strong evidence that some amount of thought went into all of this weird stuff. Because there are a lot of accidentally works here. There are a lot of like subtle bugs that turned out not to be serious, even though by all rights they should have been. So, yeah, I don't know what evidence to draw from that. It would like one idea maybe is that Bitcoin was designed by a number of people bouncing ideas off of each other, but like the code has a pretty consistent style in the early days, or lack of style. So I don't know. It's all lost to time now. But let me move on to Miniscript. Are there any more questions about script or its historical oddities? Cool. So, in practice, what script is actually used for are signature checks, hash locks, checks, and time locks. Okay, this is what Lightning uses, this is what atomic swaps use, this is what escrow things use, like bit-rated, this is what split custody wallets use, this is what like split custody exchanges, like Arwin use in Boston, this is what Liquid uses, this is what anybody doing something interesting with Bitcoin script, chances are you've got like something interesting, else some like time lock is just like a couple lawyers with YubiKeys. And all of these things fit into this paradigm of signature checks, hash locks, time locks, and then arbitrary monotone functions of these. A monotone function just means that you've got ands and ors and thresholds. Okay, you've got like this and this or that, and like 3 or 5 of these different things. And there we go. That's all you have. So an idea for a version of script that didn't have all of these sharp edges, and that didn't that allowed analysis, is what if we just created templates of all of these things? So what if you, as a user, would say, I want to check signatures with these keys, and I want these like hash locks, and I want these time locks, and I just want them in this particular order. Okay, I want these keys, or this key in a time lock, or this key in a hash preimage, and that's what I want. That will be my script, and I will just literally have a program that's just a DAG or a tree of all these checks in various ways of combining. Okay, and then now you can reason very easily about the semantics of that. You just literally just go through the tree. You just traverse through the tree and check that every branch has the properties that you expect. So if there were a way that we could create script fragments or script templates for these 3 primitives, these particular checks, and then also create script fragments that represent ands and ors and thresholds, and we could do this in a way that you could just plug them into each other, then we would have a composable script subset that was actually usable on the blockchain, and which we could reason about in a very generic way. And that's the idea behind Miniscript. But as we'll see, there are a number of design constraints. The biggest one, though, is that we wanted something that was reasonably efficient. There's kind of a naive way to do this, where you take like a bunch of check sigs and hash preimage checks and stuff, and then you write different ways of composing these, and the result is that for every single combinator, you're like wasting 5 or 6 bytes, just doing a bunch of opcodes to really make this composable, to make sure that no matter how your different subsets are shaped, that you can still do this reasonably. We didn't want that. If you're wasting 5 or 6 bytes in every single one of your UTXOs, that's going to add up in terms of fees. even if it doesn't add up, someone's going to say that it adds up, right? You couldn't do something like this in Lightning. You can't say we're just going to gratuitously waste several bytes on every single HTLC just because it gives us this general tooling. Similarly, in any other specific application, you're not going to gratuitously waste these extra bytes, because what do you get for this? Well, if anyone was using this, you'd get the interoperability and you'd get like standard tooling and all that good stuff. But nobody's going to go first because it's less efficient than what they have. So we really have to match or beat the efficiency of stuff that's deployed. And as I talk about in my more public-facing talks, like we did actually accomplish that really well. But here we go. So let's go through a lot of the problem that we encounter with this approach. So one of them. So here, ideally, like here's an example of our original vision for Miniscript. You see, you've got like an and we've got some pub key checks, and you've got some ors, and that older is like a time lock thing going on. And if you wrote this out as a tree, you could clearly see where everything is. When there's a bunch of parentheses, it looks like Lisp, and it's hard to tell what matches what. The idea was you would take this thing, and it would just map directly to script. Okay. And so one problem with this approach is that there's actually many different ways to write each fragment. There are a number of ways to do a key check, right? You can use a checksig opcode, you can use a checksig verify opcode, you can use check multisig with like one key or something weird. There are a couple different ways to do your time lock checks, and then there are many different ways to do ands and ors and thresholds in Bitcoin script. There are just a whole bunch of ways, and I'll talk about this a little bit. So maybe that's not so bad though. Right? Maybe we have like 5 different ands, and okay, so now instead of writing and at the top line of that slide, I have an and then I just have a tag, like and 1, and 2, and 3, and each one represents a different one. And then okay, I mean, that's not so elegant, but it's still human readable, it's still very easy to reason about, and it still gets you all these nice benefits of Miniscript. A related problem is that these different fragments might not be composable in a generic way, right? If I've got a checksig, that's going to output 0 or 1, depending on whether the signature is correct. If I've got a checksig verify, that's going to output nothing, or it's going to abort my script. So there's no AND construction that you can just plug either of those into. Right? Your AND construction needs to know what's going to happen if your thing passes. Right? You might have an AND that expects both your things to either pass or abort the script, and you can do an AND that way just by literally running each check in a row. Right? If the first one fails, your script aborts. The second one fails, your script aborts. Otherwise, it just runs through. Great. But if your opcodes are like leaving extra 1s and 0s on the stack, you can't just compose them. You've got to run the first one, deal with the one that's out there, maybe like op swap it out of the way, or maybe move it to the alt stack, and then run the other one, and then do like a bool and or something to check that both ones are okay. Okay, that's also fine. Again, we can just label things. Another problem though is when deciding between all these different ways to write ands and ors and stuff, there's trade-offs to make. Some of these have a larger script pub key. They're larger to express. Some of them have larger satisfaction sizes. Maybe you have to like push 0s or 1s because they've got if statements in them. Some of them have larger dissatisfaction sizes. For some of them, maybe you can just push a 0, which is an empty stack element, and it will just skip over the entire fragment. You don't have to think about it. For other ones, you've got to like recurse into it and like 0 out every single public key. And so your choice of which different and or to make depends, well, your choice of which different or to use. In an or, your choice of which fragments to use for the children of the or depend very much on the probability that certain branches will be taken in real life. If a branch is very unlikely, you want to make its script size very small. You want to make its dissatisfaction size, if that's relevant, very small. And your satisfaction size, you can make it as large as you want, because the idea is hopefully you'll never use it. Okay, and if you're using it, you're in an emergency mode, and maybe you're willing to waste a little bit of money. But now this means that your branches need to somehow label the probability. And so now the mapping between this nice elegant thing at the top, maybe with tags, and Bitcoin script is no longer two-way, right? And I remember spending, in the very early days of Miniscript, I think in the first 36 hours, we ran into this problem. And Peter was telling me, like, we need to have like a separate language that we can compile to Miniscript, and we're going to have 2 languages that both kind of look the same. And I put my head in my hands, and I said, no, this is ruined. This is not what I wanted it to be. Like, this is not what I wanted it to be. And I had a bit of a breakdown over this, because what an elegant idea, right? That you could just have this language where you can just see the policy, and then that directly maps to script, and you could pull these policies out of the script. And then all of a sudden there's this weird indirecting, and Peter, for the entire time, was trying to write this optimal compiler, and I did not care about the compiler at all. I just wanted a nice clean way to write script, and he was turning the compiler into this first-class thing. Anyway, this is in fact where we landed. Okay, and then you'll see over the next slide. The result is actually reasonably elegant. And then one final problem. Well, there's a few more on the next slide, but the last problem on this slide is that actually figuring out the optimal compilation from this abstract thing at the top to what we represent in script, there are optimizations that Miniscript can't handle, and that just as a design necessity of Miniscript it can't handle. In particular, if you reuse keys, like the same key multiple times in some weird script, like maybe it appears as a check in one branch, but then you have the same check in another branch, maybe there's a way to rearrange your tree, to rearrange your branches, so that you get logically the same function, but what you express in script is slightly different. Maybe the key appears once instead of twice, or twice instead of once, or something like that. There are two problems with this. One is that verifying that the result of these transformations is equivalent is very difficult. You're right, given two programs, or two logical predicates prove that they're equal on all inputs. I believe that's NP complete. The only reason it might not be is because we're restricted to monotone functions, but I don't actually think that changes anything. I think that's actually program equivalence. Maybe it's halting complete. It's definitely not halting complete for Bitcoin script because you don't have loops, but it's hard.
Isn't that the motivation for Miniscript to make that possible?
Right, yeah, in the original Miniscript, the motivation of Miniscript was to make this kind of analysis possible. So what we said was basically, don't reuse keys. We cannot do what we call common sub-expression elimination in Miniscript. And basically, if we wanted to do those kinds of advanced optimizations, we would lose the simplicity and analyzability of Miniscript. And as far as we're aware, like nobody's really chomping at the bit to do this. All of our Blockstream projects work with this current paradigm. So does Lightning. So does the atomic swap schemes that people are doing. So do like escrow schemes. So do like various split custody schemes. Like everything that we're aware of people doing will work in this paradigm. And so, if our goal is to get enough uptake that there will be standard tooling and standard, I mean, ultimately the goal is to have standard tooling, right? Because that's the benefit of Miniscript, is that you write a script in Miniscript, you just grab something off the shelf, it will deal with your script. It will give you fee estimations. It will create your witnesses for you. You can use it in PSBT with other things. You can coin join with other things. You don't need to write a whole bunch of script mundane code for it. And so these advanced optimizations would in theory get you stuff, but it would get you stuff in a very difficult, it would be very difficult and ad hoc to implement, and it would break these properties that we think are important for adoption. So I threw it in there, but we're not actually going to fix it. Maybe there'd be like a Miniscript 2 that would not really resemble Miniscript that could do this.
I saw a conversation on Reddit between you and Peter, I think Greg as well, that said the current Lightning script had no analog in Miniscript. Something like about HDLC switching on a pub key hash or something like this.
Yes. Okay. So this is cool.
Still relevant?
No. So this is really cool. The question is about Lightning HDLCs not having any analog in Miniscript. So in Lightning HDLCs, you have a pub key hash construction, and if you reveal the preimage to a certain hash, this needs to be a public key, and then there's a signature check that's done with that public key. And if you don't reveal a preimage to that hash, then you just sort of like switch on that and you do something different instead. In the original version of Miniscript, we had no notion of pub key hashes. So you just like couldn't do this. And then in May of last year, Sanket Kandalkar joined us at Blockstream as an intern. And he said, guys, what if we do a pub key hash construction? And there are lots of like my head and my hands kind of reasons not to do this for complexity. But Sanket should know if we add this, we would need to change up our type system a little bit, and I'll talk about that in a few slides. But then we will get a Miniscript expressible version of Lightning HDLCs. Both of them, there's two. There's one that you keep on the local side and one that's remote. And on one of them we save 7 bytes, and on the other we save 17 bytes, versus the deployed Lightning HDLC. So we actually went from being unable to express what Lightning does without like unrolling it into a very inefficient thing, to having a more efficient way to express what Lightning does in Miniscript. Now, it's still incompatible with what Lightning actually did. So one goal of ours was that you could take the HDLCs that are actually defined in bolt 3 or bolt 7 or wherever they are, and in 3? Thanks. In bolt 3, and just interpret those as Miniscripts. And we can't do that because of this switch behavior, because Miniscript doesn't really have a way to say, like, if a preimage is present, use it as a public key, otherwise use it as a reason to do something else. And that, I think adding that to Miniscript would be technically possible, but it would add complexity to Miniscript, and all we would gain was the ability to interpret HDLCs as Miniscripts. And it's unclear where the value is to either Miniscript or Lightning, because Lightning already has a bunch of special purpose tooling. Like, the idea behind Miniscript is you're trying to express the conditions under which coins can be spent. Whereas the idea behind a Lightning HDLC is you're trying to use the blockchain to constrain like an online interactive protocol, right? And those are kind of conceptually different things. So it probably doesn't make sense to use Miniscript inside of Lightning, unless it was really easy to do. Like, you would save some code deduplication, but like, you need so much extra code to handle Lightning properly anyway, that the script manipulation stuff is kind of a minor thing.
It might be useful if one side of a channel is a multi-sig setup and doesn't want to bother the other side with the fact that it's a multi-sig setup.
Right, yeah, okay, so the core developer in the back points out that it would be useful if you could have a Lightning HDLC where the individual public keys were instead complicated policies. There might be like multiple public keys or a check multi-sig or something. And that's true. Yeah, if you could use Miniscript with Lightning HDLCs, then you could have two parties open a channel where one person proposes an HDLC that isn't actually the standard HDLC template. It's an HDLC template where the keys are replaced by more interesting policies, and then your counterparty would be able to verify that. So that's true. So that would be a benefit of using Miniscript with Lightning. Yeah, and then there's a trade-off between having that ability and having to add special purpose Lightning things into Miniscript that would complicate the rest of the system. Yeah, and maybe we made the wrong choice on that trade-off, and maybe we want to extend Miniscript.
So it depends if the scripts are going to be regularly redesigned, or if there are going to be different alternative paths in future, or if there's contracts on top of Lightning. I know Z-Man's talked about like arbitrary contracts, which potentially could be script or Miniscript on top of Lightning.
Yeah.
Well, I think you can use scriptless script to express everything you want and run it on top of Lightning.
Right. So yeah. So there's another thing is that Pedro and Guido and Aniket and everybody and me have the script scheme. I think that's public now, or will be soon, where you can do all sorts of like really complicated policies with scriptless scripts. So if we're going to overhaul Lightning anyway, what if we move to scriptless scripts instead of Miniscript? And that's like kind of moving in the opposite direction, like towards more complicated interactive things, rather than like off-the-shelf like static analysis things. And so yeah, so that's another observation, is that the impression I get from the Lightning community is that there's more excitement about the scriptless script stuff, which has a whole pile of other privacy and scalability benefits, than there is excitement about Miniscript, which really. And I think maybe this comes down to Miniscript being targeted at spending policies for coins that mostly sit still. Maybe, or maybe they don't mostly sit still, but it's about spending policies rather than constraining a complicated protocol, is my view of the way different people think about this.
I did see Connor and the R&D team had used Miniscript to optimize some new Lightning scripts. Did you see that?
Cool, I did not. Yeah, so there's a claim is that Connor used Peter's website or something to find a more optimal Miniscript.
They
Nice.
saved some bytes on
Yeah,
some
awesome.
new Lightning scripts.
I've heard this from a couple people. Apparently Arwen, which does a non-custodial exchange, had a similar thing where they encoded their contract as a policy and then ran it through Peter's website and they saved the byte. This happened to us at Blockstream as well for Liquid. We had a hand-optimized script in Liquid that is deployed on the network now, and Miniscript beat it, which is kind of embarrassing for all of us because, I mean, we're supposed to be the script experts, aren't we? Yep, but in any case, where we landed is we don't have explicit Lightning support. We could be I could be convinced to add it. It's just a pain in the ass, and it will lengthen the length of the website by like 20%. Which has a trade-off in uptake and complexity and so forth, but we could be convinced to add it. We're also not going to solve this common sub-expression thing. That's beyond like adding a few things, and that's really completely changing how we think about this. Okay. I have another category of problems here that I'm going to call malleability. And let me check on my time. Shit, I'm above an hour. So malleability. So as a quick bit of background, malleability is the ability for a third party to change the witness that you put on a transaction. So prior to SegWit, if somebody did this, they would change your transaction ID and like completely break your chain of transactions, and it was just a huge mess, and this was very bad. After SegWit, the consequences are less severe. If somebody is able to replace your witness with another valid witness, they may be able to mess up transaction propagation or block propagation because it will interfere with compact blocks. It may also change the weight of your transaction in a way that your transaction is larger than you expected, so the fee rate you put on it is going to be higher than the fee rate that the network sees, so you're going to wind up underpaying because some third party added crap to your witness. So we really want things that Miniscript produces to be non-malleable. And an interesting observation here is that malleability is not really a property of your script as much as it is a property of your witness, or your script plus your witness. The reason being, when you create a full transaction with witnesses and stuff, the question you ask is can somebody replace this witness with a different one? Okay? And it turns out that for many scripts, like there are some witnesses you can choose for which the answer is yes, but there are other equivalent witnesses you can choose for which the answer is no. Okay? And that's something that there's a lot of complexity involved in that we didn't expect going into this. And that's kind of a scary thing, because when there's complexity in satisfying scripts that we didn't even think about before Miniscript, that means that this has been hiding in Bitcoin script all along, and every usage of script like accidentally has had to deal with this without being able to think clearly. Yeah, and then there's some complexity about what malleability means. One thing is that the ability of third parties to change things depends a bit on how much they know. Like, do they know the pre-image to some hash that's out there, for example, and can they just stick that on the blockchain? If you have a time lock somewhere in your script, and this is covered by a signature, then the adversary can't change it, because time locks are encoded in your sequence or lock time field, and those are signed. But if it's not covered by signature, then maybe somebody can change that and then change branches. You know, it's actually a little bit difficult to...
we don't have SIGHASH to not sign time locks?
That's correct, yeah. We do not have a sig hash that won't sign time locks, but you can create miniscripts that just have no signatures, right? And then there's a form of malleability that appears. So this is a little bit difficult to reason about, although we've eventually, Peter and I settled on something that's fairly coherent. A long argument I had with Peter was about whether it counted as malleability if like other participants in your transaction are able to sign things. I wanted to like mark certain keys as just like being untrusted, and we consider like signatures appearing out of nowhere. Peter argued this didn't count as malleability. I think Peter won that. I'm not going to rehash that entire argument, but I think there's maybe a simplicity of reasoning where if you can say like this key is untrusted, and then use all your standard malleability analysis to decide what's the worst that can happen to your transaction, that might be useful in some cases. But I think that's a technical thing, and then Peter argued that that's an abuse of the word malleability, and maybe I can share algorithms, but I shouldn't be arguing this in public, so I won't. So, all this said, this just covers some simple things. So, to make our task tractable here, we're going to assume standard policy rules. I talked about size equal verify earlier. There's a policy rule in Bitcoin, meaning a standardness rule that affects transactions on the network, called minimal if. That means that what you put as input to an if or a not if, or an if stop, no, just if or not if, has to be 0 or 1. So you do not need size equal verify. The node will enforce that the size equal verify is done. We're just going to assume the standardness. We're going to say if something's malleable, but you have to violate standardness to malleate it, then that doesn't count for our concerns about transaction propagation. If your only potential attackers are miners, miners can already mess up transaction propagation by like creating blocks full of secret transactions and stuff like that. So that we're just not going to deal with that. That will save us a whole bunch of bytes in like almost every fragment. And in particular, enforcing that like signatures either have to be valid or they have to be zero-sized is very complicated and wasteful to do directly in script. But there's a standardist rule that requires signatures be either empty or valid. As I mentioned, we don't handle common sum expression. Yeah, and this just, it would conflict with this model where you have just a tree that you can iterate over. That like clearly your script corresponds to some tree and vice versa. And to retain that, we can't be doing complicated transformations. We also assume that no key reuse occurs for malleability, okay? And so here's something where like you have two branches, the same key is there. If you provide a signature for one branch, then absent using opcode separator, say, which is also expensive, somebody could take that signature for one branch and reuse it in another branch. And so now there's potentially a malleability vector where somebody could switch which branch of an OR statement is being used. And I think we have to assume no key reuse, because it seems that in general, if you can have arbitrary sets of keys that intersect in arbitrary ways in conjunction with thresholds, again, it seems intractable. This one doesn't feel NP hard, but we don't know how to do it in like sub-exponential time, so it's possible that it is. Okay, so those are our three ground rules for Miniscript. We're also going to separate out Miniscript. Miniscript directly corresponds, it's just a mapping between script and something human readable. Okay, and we're also going to have this policy language. The policy language has like probability that different branches are taken, basically. So Miniscript has all the like weird tags, like and1, and2, and3, and so on. They have better names than that. The policy language has probabilities. Okay, so given a policy, you can run it through what's called a compiler that will produce a Miniscript. It will look at your probabilities. It will decide what the optimal choice of a specific Miniscript fragment is. It will output a Miniscript, which is clearly semantically identical to the original. This is very easy to check, by the way. You take your policy and delete the probabilities. You take your Miniscript and delete all the tags, and those will be like equal. Okay, that's how you check that your compiler output is correct. Okay, that's a really powerful feature, right? That means you can take stuff on the blockchain, decode it into a Miniscript, lift it into a policy by deleting all the noise, and then you can see immediately what it's doing, okay? But then Miniscript is sort of where all the technical complexity is, right? We have all these different tags that need to compose in certain ways, and this is what I'm going to get into that I haven't really gotten into in any of my public talks here. Here's a policy. Rather than writing it in the Lisp format, I drew this pretty picture like a year ago that I've kept carrying around. Here's the same thing compiled to Miniscript, okay? So at the bottom of this slide there, I've written the actual script out in opcodes, but you can ignore that. You can see that the difference between these two, there are two differences. One is that I've attached all these tags to like ands and ors, like an and v and or c. I think are the current names for them. The other interesting thing is like the PK in the left. That says checking pub key 1, I've added a C there. And that's saying there's actually a public key, but then also I stuck a checksig operator in there. And there's JV, and V means there's an op verify at the end of this hash check, and the J means that there is some complicated check that basically skips over the whole check if you give it an empty string, meaning like no preimage, and otherwise we'll do the check. And so that's, that J is needed for anti-malleability protection. And then we've got these B's and V's and stuff, which I will explain in the next slide. These are types. So Miniscript, unlike script, has a type system. And to have a valid Miniscript, you need these types. And you need to do checks. So let me justify that real quick. So as I mentioned, you've got some opcodes like checksig, they push 0 on the stack but 1 on success. You have other ones like checksig verify, which push nothing on success and they abort your script on failure. You have all these expressions that wrap things. Of course, there's the composition ones, there's the ands and ors and thresholds, but then there are also like these J's and V's and C's and all these little wrapper things that manipulate your types. And they might behave differently depending on whether you've given a checksig or a checksig verify, or whether you've given something that can accept 0 as its input, or something that can't ever accept 0 as an input, or something like that. So basically we have these 4 base types, B, V, K, W. So B is just base, is what we call it. This is something that will have a canonical satisfaction that will result in pushing 1 on the stack. It has a canonical dissatisfaction, which will push 0 onto the stack. Or does it? Oh no, it doesn't necessarily have that. That's later in the. So the only rule is that it has a canonical dissatisfaction, which pushes a non-zero value on the stack. And if it can be dissatisfied, it will push a 0 on the stack. And then we have this v, which has a canonical satisfaction that will push nothing on the stack. Okay? And then there are no rules beyond that. And if you do something wrong, you abort. I don't need to say. Basically, all of these things have this kind of caveat. If you do something wrong, it will abort. Okay? And I have this weird one, k. This one, if either you satisfy or dissatisfy it, is going to push a key onto the stack. But sort of whether you satisfy or dissatisfy will propagate in kind of an abstract way up to your check sig operator that will turn that key into either a 0 or a 1. And then you've got this weird one, w, which is a so-called wrapped base. This is used for when you're doing like an and or an or, and you've got a whole bunch of expressions in a row. Basically what a wrapped expression does is it takes the top element of your stack, it expects that to be some sort of accumulator, 0, 1, 2, 3, 4, 5, just some count or whatever. It will move the accumulator out of the way, it will execute the fragment, it will bring the accumulator back, and it will somehow combine the result of your subexpression and the accumulator. Okay? And typically it does this by moving the accumulator to the alt stack, moving it back when you're done, and then combining them using op-and, or boolean, bool or, op-add in some cases. Then we've got these little minor type modifiers. And we've got 5 of them. I was going to go to the website and like read through all the detailed justification for these, but I think I'm actually not going to do that. They're just sort of minor things like the O means 1. It means that this is a fragment that takes exactly one thing from the stack, and this affects the behavior of certain wrappers. Okay. And the idea behind all of this is that if you have a Miniscript program, you can run it through a type checker that assigns all of these tags and type modifiers and stuff to your program. And if your top level program, if the root, if this top and here is a B, you have a valid Miniscript. If it's not a B, it's an invalid Miniscript. All bets are off. Probably it can't be satisfied. Okay, and this type checking, there are very simple rules. This is linear time. There are very straightforward rules for propagating these types up. Okay. And there's a giant table on Peter's website, whose link is right here, which describes exactly what these mean and what the rules for propagation are. But you as a user don't really need to care about that. All you need to know is when you run the type checker, if you get a B at the top, you're golden. If you don't, then you're not, throw it out. And if you get your Miniscript by running our compiler, then it will always check type check, because our compiler enforces that type checking happens. Okay, so all of these complicated questions of correctness are now wrapped up entirely in this type system. You have 4 base types and there's 5 modifiers. Okay? Peachy keen. We've got another type system in parallel for malleability. And this also was something that we got pretty far into the project before we realized that we needed to separate these things out conceptually. The malleability, as I mentioned, is this ability for a third party to replace valid witnesses with another valid witness. One complicated thing that we didn't realize until later is that we have a notion of like canonical witnesses that we expect honest signers to use. So like if you have an or, like 2 branches, you have either satisfy like this subscript or this other subscript. There's some forms of or where you just try to run both of them and then you check that one of them succeeded. And any honest user is just going to pick one or the other and satisfy it, right? And dissatisfy the other one. But somebody being dishonest could satisfy both. And that would still pass the rules of Bitcoin script. And when we're thinking about malleability, we have to consider dissatisfactions like that, okay? So that was annoying. There's suddenly this whole wide set of possible behaviors in Miniscript that suddenly we had to consider when doing malleability reasons, okay? What else? Okay, there are bad things about malleability, particularly the effect transaction propagation, the effect fee estimation. Those are the bad things about malleability. Okay, so what question can we ask? So can we assure that all witnesses to a script are non-malleable? This is a wrong question to ask, it turns out. So I mentioned that malleability is a property of witnesses, not scripts. But even so, it's not necessary that every possible witness be non-malleable. What we want is the second thing in red here. Basically, no matter how you want to satisfy a script, no matter which set of public keys or hash primitives or whatever, you want there to be some witness you can create, even if it's a bit expensive, that will be non-malleable. And our compiler will ensure that this is true. If you give it a given policy, it will make sure every single possible branch of that policy has a non-malleable witness that can be created. Okay, and this was like quite difficult and non-trivial, and this is a source of a lot of the security bugs that I found when auditing just random crap that I found on the blockchain. As it turns out, curiously, the Tier-Nolan atomic swap protocol from 2012, 2013, that's actually okay. And Lightning is actually okay. Yeah, and that was surprising. And I think the Lightning folks kind of got lucky in some ways. I mean, no, there was a lot of thought that went into Lightning. But this, the way we're thinking about this here is like a very structured way where we can even reason about this in an automated fashion. So it's great that we can do that now, and that provides a lot more safety and assurance. And what I found very frequently when trying to use Miniscript internally at Blockstream to optimize Liquid and to optimize various things I was doing, I was like, wow, I have Miniscript, I can do all these powerful things. Now I can just optimize the hell out of my script and fearlessly just like do things. And every time I would find an optimization, my analysis tools, the compiler, would reject it. And I'd be like, oh, this is broken, another bug in Miniscript. And then pretty much every time, it was not a bug in Miniscript. I would chase through the logic, and this is a difficult problem of how to get good error messages. But when I would trace through the logic of why it was failing, it would come down to me violating one of these malleability properties. And I would find some attack that was actually being prevented by my Miniscript analyzer, warning me that, hey, you've got like a bare hash preimage sitting over here, and if that hash becomes public, someone can throw away the rest of the witness and use that, for example. And so we have these 3 extra type modifiers. We have those 4 base types, 5 modifiers represent correctness. We have 3 more for malleability. S means there's a signature involved somewhere in the satisfaction. It used to stand for strong, and then it used to stand for safe. We had all these weird notions. Now it's just, if there's a signature, that captures the properties that we need. There's this weird thing called F for forced. What that means is that there's no way to dissatisfy it, at least not without throwing a signature on there. So no third party can dissatisfy something that's an F. And then there's an E, which is in some abstract sense the opposite of F. In E, you've got a unique dissatisfaction that has no signature on it. So a third party can use that unique dissatisfaction, but if you dissatisfy it, then that's the only dissatisfaction. So if you're not satisfying this, then a third party can't do anything about it, right? They see the dissatisfaction, they have no other choices, okay? And again, I'm going to bump over to the website in a sec, but I'm not going to go into there. Basically, it's got a table of what these rules mean, how they propagate, what the justification for it is. And it's also got a summary of this slide here, which is how do we produce a signature? So I've been sort of hinting at various malleability vectors. And there is a question, so suppose you have a Miniscript that is something like, take either this time lock or this time lock, and combine it with a public key. This is malleable, because an attacker, wait, it's actually not, because the signature is going to cover the specific. Okay, this is complicated. I should have chosen a simpler example.
You can't, because the signature is going to cover it.
Yep. So the signature will cover the lock time, but if the lock time is high enough that it actually satisfies both branches, then if you've got like an op-if.
Oh, if it's already an already spent time lock or a time lock in the past.
Yep. Yep. So if you try to use the later time lock, right, then you put a time lock that will be greater than both restrictions. Now, if you're switching between those using the op-if or something, a third party can change your 0 to a 1 and swap which branch of the op-if you're using, and that's a malleability vector. And so naively, oops, I have a work call right now.
It's going to fail. I mean, the transaction is going to fail on the end lock time check.
So
not done on the script evaluation.
So it's not going. So in this example, I'm assuming the lock time is satisfied. Okay. So if you actually satisfy this lock time, so there exists a branch in your script that if somebody honestly tries to take, the result will be a malleable witness. Because you're trying to take the later lock time, and some third party can change it so you're taking the earlier lock time. Okay. And we spent a lot of time iterating to try to prevent this from happening, because it's actually quite difficult to reason through why exactly this is happening. Because as the Lightning developer is saying, you do have a specific lock time in the transaction that's covered by the signature. So where does the malleability come from? Where does the malleability come from? And the answer in Miniscript parlance is that you have an if statement where neither of the two branches have this S property, signature, on them. And if you ever have an if statement or a threshold where there are multiple possible paths that don't have the S on them, that's illegal. Like, you have to dissatisfy that. You aren't allowed to take either time lock, because if you do, the result is going to be malleable. And then if you have to dissatisfy it, and then you don't have the E property, then probably your whole script is going to be malleable, because even after dissatisfying, if you're missing E, that means that somebody else can dissatisfy. So actually all of these rules have simple propagation rules that they're very difficult to convince yourself are correct, but which catch all of this complicated stuff. And so at signing time, how do we avoid this? How do we say, oh, I've got this weird branch here, where maybe, and maybe it's not a time lock, maybe it's a time lock or a hash preimage. And now I need to think, well, I'm only allowed to take the hash preimage if the time lock has not yet expired. Because if I try to use a time lock, if I try to use a hash preimage after the time lock has expired, a third party can delete the hash preimage, take the time lock branch, and there's a malleability vector. Okay? So how does my signing algorithm reason about this? How can I actually produce a valid signature and not get any malleability under these constraints? The answer is, basically you go through your script, you recursively go through your Miniscript trying to satisfy every sub-expression. You satisfy every sub-expression, then you try to satisfy like the and or however these are combined, and you propagate all the way to the top. And whenever you have a choice of satisfactions, you look at what your choices are. If they all require a signature, that's great. We don't need to think about malleability, because nobody can change those. They would need a signature to change things up. And we assume those signature reuse, we assume that third parties don't know your secret keys and so on.
No Cgash?
So in Miniscript we only use Cgash all. Okay. That's a good point from the audience, that different Cgash modes might complicate this. But in Miniscript we only use Cgash all. Okay, so if they all require signatures, that's great, you just take the cheapest one. Okay, that's what you want to do. If there's one possibility that doesn't require a signature, now you need to be careful, because a third party can go ahead and take that. So now you can't take any of the signature ones, you have to take the one that the third party can take. Okay? And the reason being that you have to assume a third party is going to do that to you, so you have to get in front of them. So you just don't publish any of the signature requiring ones. And so this may actually result in you creating a more expensive satisfaction than you would if you didn't care about malleability. So there's some context I can imagine. Well, there's no context I can imagine where this is safe, but you may want to use a malleable signer, and maybe you could save a few bytes, but you need to really be careful doing that. Okay, and then if there are multiple choices that don't have a signature, then you're SOL, because no matter what you choose, a third party is going to have some option. And that's basically all there is to this. You have these rules for E, F, and S that propagate through. Using those rules at signing time, you apply these 3 points, and you can recursively generate a signature. Okay? It's pretty great. And this was a really complicated thing to think about and to reason through. And it's really cool that we got such a straightforward algorithm that will handle it for you. And when I talk about our analysis tools catching me trying to do dumb stuff, this is what I mean. I mean, I would try to sign, and it would refuse to sign. And I'd trace through, and I'd be like, what's wrong? Like, did I give it the wrong keys? Like what's going on? And eventually I would find that somewhere I would have a choice between two things that didn't have signatures, and it was parsing on that. So that's really cool. So it's something that has actually saved me in real life. Although, only from saving me from wielding the power Miniscript gives me in unsafe ways. So, it's good. That's a good thing.
Does any of the tooling have ignore malleability mode? Like, if I wanted to make it malleable because, say, I'm a minor and this transaction won't be published?
Yep. So the question is, does the tooling have a non-malleable mode? And I think Peter's code does. And I forget, we might have an open issue on Rust Miniscript to add this. It's a little bit more complicated than just disabling the checks, because you might also want to take some of these non-canonical satisfactions in that case, so you can imagine cases where they're cheaper. But I think Peter implemented it, but Sanket and I didn't. But yeah, there will be. That is a design requirement for a finished Miniscript library, is that you can enable malleability if you want. Okay, I have a link to the website. I was going to go through this in more detail, but I'm not. You can see I'm burning everyone out already.
I'm happy to help you get on. Should I I get the website up?
Yeah, sure. Well, let me run through. I've only got a couple more slides, actually. So let me run through my last subject here, which is fee estimation, which I should have tried to move sooner, because this is actually no, it's not the most technical. Malleability was the most technical. Let's think about fee estimation, and I'll be a bit more high level and a bit more friendly for these last few slides. The fee estimation requires similar reasoning to malleability. You've got to go through your transaction. You've got to figure out what is the largest possible witness size that might exist on these coins. Okay, and that witness size, the largest possible witness size, is what I have to pay for. So if I'm in control of all the keys, I can do better. I can say, well, I'm not going to screw myself, so I should actually just find the smallest satisfaction that uses the keys that I have. But if I've got other third parties who might be contributing, I have to consider the worst case of what they do. They might be able to sign, they might not. Maybe that affects how efficiently I can sign something. Regardless, there's a simple linear time algorithm I can go through where I just tell it which keys are available and which ones aren't. Or no, I think I have to assume all keys are not potentially available before it gets complicated. A simple linear time algorithm, it will output a maximum. I know the maximum size of my witness, and that is how much transaction weight I should pay for when I'm doing my fee estimation. Okay? This is great, by the way. This is the worst thing about Liquid. We had like half of our development effort going into figuring out fee estimation. In Liquid, we have the ability to swap out quorums. So we have coins in Liquid that some of them are controlled by different scripts than others. And we have this like joint multi-sig wallet trying to do fee estimation and cross-checking each other's fee estimation on coins with complicated scripts that potentially have different sizes of the witnesses. And with Miniscript, we just call a function. We just like get maximum witness size, and it just does it for us. It's really like Miniscript was really just a Peter and I going off on a bender, but we really wouldn't have been able to do Liquid without it. So we got lucky there.
So they need to try to maximize it. They just need to make it bigger than what the honest signers.
Yeah, that's correct. Yeah, you need an overestimate is what you need. And yeah, and you can overshoot, that's perfectly fine. But if you undershoot, you might be in trouble because your transaction might not propagate. You've also got to consider malleability when you're considering, well, you don't really. So if you run through your script, you do your type inference, and your top level thing has an S on it. That means that you it has an S and an M on it, I think. Or an N, I don't know. If you run through the type checker and it says it's not malleable, you don't have to think about malleability. That's awesome. If you're being weird and you want to have potentially malleable scripts, then that will complicate your fee estimation, but again, it's doable. You can just run through this in linear time. Okay. And let me talk a bit about how these malleability and fee estimation work. And this is one security vulnerability that I found on the blockchain, and you could argue this is irresponsible disclosure, but I mean, like, saying it's on the blockchain and giving a script that's not even the exact script. If you guys can find this, you could have found it without me. So suppose you have this kind of atomic swap thing. So you've got these coins that can either be spent by two parties cooperating, or another party can wait for a time lock. Or sorry, it can be spent by one party by revealing a hash preimage, or after a timeout, the second party can use this time lock. Okay. The issue here is that this time lock thing is actually not under control, or sorry, the hash preimage does not have any, party B is not required for this at all. So suppose the time lock expires, okay? So party B creates this transaction using the time lock case, publishes this to the network. Party A sees this and has eclipse attacked party B. Party B replaces the witness that was using time lock with one that uses the hash preimage. Okay, so they're actually following the atomic swap protocol, but at this point, party B has given up, right? They're using the hash preimage, they're no longer waiting for the hash thing, they're just trying to back up. Party A uses the hash preimage to increase the weight on the transaction, causing it to no longer propagate and no longer get into the next block. Then party A can go wait out the time lock on the other side and steal the coins. Okay? And the solution to this, using Mini, so there are two solutions to this. One is party B, when doing fee estimation, should just consider that A's key is not under his control, and then consider worst case behavior from A. Okay, and that will do the right thing, because then party B is going to wind up paying a higher fee, but they're paying a higher fee to prevent this attack. Another, yeah?
The real attack is stacking the transaction in the mempool, not because I can always I can always drop the signature for the weakness, or I can.
Right. Yeah. Yeah. So the real attack here is that I've gotten the transaction in the mempool
Yeah.
with a specific TXID, but
Yes,
with a lower
because
fee
you
rate.
don't track by weakness transaction ID right now.
Yeah, that's correct. And I don't think we want to.
CRC is working on some change.
There's a PR to do transaction related
Yeah, but not the mempool.
WTX IDs. So
Okay, cool. So if the network was looking at WTX IDs, that would also prevent this kind of thing. And then another solution is when creating the transaction, party B could go over this and ask the question, is my signature required for every branch of this? And in the standard Tier-Nolan atomic swap, that's actually, the answer to the question should be yes. The second party, well, they're ordered in some way, but basically, the party who has a time lock should have to sign off on all branches. And that's very easy to check with Miniscript. Linear time, you just scan through the script, you look at every branch, say, is my key in every branch. Party B does this, and if party A had proposed this broken thing, B would just reject it out of hand. So there are a number of ways that we can address this concern, and Miniscript gives you the tools to do them. So that's good. This was something that I hadn't really considered. It's a little bit contrived, but not a lot contrived. I mean, if you can only decrease the fee rate by a little bit, and your goal is to decrease the fee rate by enough that you stall a transaction for so long that a different time lock expires, and the other party doesn't notice that you put a hash preimage that they can use to take coins in the mempool. And it's a little bit contrived, but you can imagine this reflecting kind of a wider issue where you make incorrect assumptions about how your witness size might grow because other parties are not cooperating with you. And Miniscript gives you the tool to reason about that. Okay. So I've been talking about keys being sort of trusted or untrusted up to this point, right? If a key is yours, you can assume that you're always going to do the best possible thing. If the witness is smaller by signing with it, you'll sign with it. If the witness is smaller by not signing with it, you won't sign with it, okay? And then you have these untrusted keys where you just gotta kind of assume that they'll do the worst thing when you're doing fee estimation. There's another dimension here, actually, about availability. If keys are definitely available, then, well, this is very similar to being trusted, right? It means, so if you trust a key and it's available, you can just do your fee estimation assuming that it will be used in the most optimal way. If the key might not be available, then you can't, actually. If it's on like a hardware wallet that maybe your end user might not have access to or something like that, then actually you've got to assume that maybe the signature won't be there and you've got to treat it as worst case. If a key is definitely unavailable, that's kind of cool, right? If the key is untrusted, but you know it's definitely unavailable because you know that it's locked in a safe somewhere and in another continent, then you can actually treat it as trusted. And unfortunately, this notion of trust and this notion of availability don't actually overlap entirely. So it turns out that if you try to use this, if you try to do fee estimation in the way I just described, it looks like it might be intractable. You've got an open problem. This is frustrating. This is why Rust Miniscript is not done, by the way. It's because every time I go to the issue tracker to go close all of my remaining things, I jump onto this, and then I don't make any progress for many hours or days, and then I have to go back to my real job. This is very surprising that this is open. We thought that we had a solution at the core dev meetup in Amsterdam last year, Peter and I, and then I think Sanket and Peter broke it the next day. It seems like we have this ability to estimate transaction weight in a really optimal way that takes into account all of the surrounding context. But then it seems like it's intractable here. And I tried to write on a high level what you have to do, and even on my high level description I was able to find bugs in. So Miniscript gives you the tools to get a upper bound, a lower bound on the worst case transaction size. And that's what you need. But what I'm saying here is that we could do even better than that by giving Miniscript tooling some more information, but I don't know how to write the algorithm to do that. So this is kind of a plea for anybody who's interested. I think you could get a master's thesis out of that. You won't be able to get a PhD thesis, but you could get, I don't know, if anyone here is a master's student, I think this is definitely a thesis-worthy thing to do. Unless it turns out to be trivial, but I'm pretty sure it's not. I tried, Peter and I tried for a while, and Peter has 2 PhDs, Okay, last slides. I'm sorry. I actually like nailed the 2-hour time limit. I was kidding. So real quick, let me just cover the interaction between PSBT and Miniscript. Okay, and this ends the technical part of the talk. And this is really just an engineering, this is just something we need to grind through. There's a couple minor things that need to be done. PSBT is, of course, Andrew Chow. He stepped out like 1 minute ago. This is Andrew Chow's brainchild. This is a transfer protocol for unsigned transactions that lets you just tack things onto your inputs and outputs and stuff. So if you're a wallet trying to sign a transaction in some complicated multi-sig thing, you don't need to think about that. You just check the transaction, you sign it, you attach the transaction to it and pass it on to the next guy. You don't need to worry about like putting the signature in the right place, like and like giving room for other people to fit it in or whatever weird stuff you might otherwise have to do. You just stick it onto the PSBT. And so PSBT has like a whole bunch of different roles. The most interesting role is the so-called finalizer. And that's the person who takes this PSBT. It takes all of the signatures that are attached to this, takes all the hash preimages that are attached to it and stuff, and actually assembles a witness. And up till now, the only way to write a finalizer is to kind of do template matching. Say like, oh, this is a normal check multi-sig, I know I need to look for these keys, and put them in this order, kind of thing. But with Miniscript, you can write a finalizer that can handle any kind of a policy that you throw at it, any kind of script that you throw at it. It will figure out whether it has enough data to actually satisfy the input and actually finalize the transaction. Given enough data, it can even optimize this. It can even say, oh, if I use these signatures instead of that signature, I can come up with a smaller witness. So your finalizer has now the ability to not only support pretty much anything that you throw at it, any protocol that anybody's using today, you can just write an off-the-shelf finalizer, maybe with some special purpose HGLC code, that will work. And it will even, the output will be more optimal than what would otherwise be done. And like maybe like a dumb example of this, I have a simple finalizer. Well, it doesn't use PSBT, but the finalizer logic in Liquid, where typically we need 11 signatures on a given transaction, and typically we get 15 because all the signers are actually online. And my code will go through and find the 11 shortest ones by byte. Okay, and we save a few bytes in Liquid every transaction. We waste a tremendous amount of bytes using, check multisig and explicit keys and all this, but we save a few bytes that way. And the reason we can do that is that I'm not writing this insane micro-optimization code for Liquid. I'm writing it in a Miniscript context where it can be vetted and reused and stuff, and it's actually worthwhile to do these sorts of things. So that's really cool. So Miniscript was designed to work with PSBT in this way. Yeah, there are a couple minor extensions to PSBT that we need, which maybe we have. There's been some mailing list activity in the last couple months, but okay, but it's not there.
All your suggestions have gone nowhere.
Yeah, I'm sorry. So I did a bad thing, and I wrote a bunch of suggestions in an English language email to the mailing list and wrote no code and never followed up. So of course nothing has happened. Now that's on me. I should have written code. I should follow up and do that, and I will when I find the time.
The point on the last slide, it's like around roles. It means that you don't have to allocate the finalizer, or the finalizer can be transferred at a later date. What's that final point? I don't understand on that slide.
Roles are a PSBT thing.
Yeah, so the roles are actually different participants. So if you are writing code for like a hardware wallet, say, chances are you only care about the signer role, right? Which means looking at validating the transaction and just producing a signature. And then you just tack that onto the PSBT, and it's somebody else's problem to actually put that into the transaction. And maybe there's another role, I forget what it's called, where you add like extra information. You say like, oh, this public key is mine, or like I know a BIP32 path for that or something. And maybe your host updater, thank you. And if you're writing host software, maybe you care about being an updater. And right now, to use PSBT at all, you kind of have to write finalizer code, because every individual person needs to know how to make a transaction. But the goal of Miniscript is that we can write like one finalizer to rule them all. Like there will be a standard Miniscript finalizer, and then nobody else in the ecosystem is going to have to deal with that again. As long as they can fit their project into Miniscript, they can just use a standard finalizer, which is great, because that removes by far the most complicated part of producing a Bitcoin transaction. And it also gets you better flexibility and interoperability. So yeah, so the different roles are actually different participants. Yep, as I mentioned, finalizing optimally, as I mentioned, it is similar to fee estimation. If you actually take all the information that's potentially available, then it becomes intractable, even though it feels like it should be tractable. That's it's a bit frustrating, but we can definitely, finalize in an optimal way, given just information about what data is actually available in the final state, right? You give it a PSVT with enough signatures and hash pre-images and whatever, and we can write very straightforward linear time code that will find the optimal witness using that data. Find the optimal non-malleable witness using that data, actually, which is a really cool thing. Although, you need to be a tiny bit careful that the finalizer has access to extra signatures and stuff that in principle the finalizer could use to malleate. So if you have an untrusted finalizer, then that's a different trust model, and you need to think about that.
Not necessarily even an untrusted finalizer.
Right, another
anyone
participant.
has the full PSVT.
Yep. Yep. So this is a point of minor contention between Peter and I. The question of how do you think about trust, like distrust from your peers when you're doing a multi-signature thing. And where we landed on for the purpose of Miniscript is that does not count as malleability. That's like a separate analysis thing that I haven't fully fleshed out, to be honest. I don't know the best way to think about that. If you actually distrust your peers and you think that they might malleate your transactions, I'm not sure in general what, if anything, you can do. Well, so it's not just not giving them all the PSP, right? They can replace their own signatures.
They can ransom change.
They can ransom,
yeah.
It gets, it's not as straightforward. There's no straightforward thing. I can find other attacks for most of the straightforward things. Okay, so this is actually the end, isn't it? Yes. All right. Thank you all for listening for almost 2 hours. I had a lot of fun doing this. I hope you guys got something out of it. So a real quick summary. There's an issue tracker on Rust Miniscript that has all of the open problems that I mentioned as just like bugs. There's also some like almost janitor stuff. In particular, like writing the PSPT finalizer. There's a couple open bugs that are actually like bugs that I need to fix. There's lots of work to do here. Well, I should say that there's a reasonable number of straightforward things that need to be done, and there's a small number, I think like 2, of hard things to be done that might be like thesis level work. So yeah, it would be awesome if somebody would do the thesis stuff, because then I would definitely finish the other stuff. And there we go. Thank you all for listening. Yeah, it's been 1 hour and 45 minutes, so we have 15 for questions if people are still awake.
Do you want the website up?
Yeah, actually, can I put the website up? Yeah, so that's...
What's Peter's repo?
What's Peter's repo? So, I don't know that Peter has a public repo yet, because his code is all like patched into Bitcoin Core.
There's a PR for that.
Is there a PR for that?
Yes.
Okay, then Peter's repo is the PR.
Okay.
Yeah. I think he has a separate repo that he compiled to WebJS or something for the website, but I think that's a private repo. Is it public now? Okay, all right, then I should add the link. What is it? Is it BitMetas?
It's one of those, this website. It's something on that website.
Oh, excellent. Oh yeah, look at that. There we go. So you can see the code that I'm hovering over. Can you see my cursor? Yeah. So that one is Peter's website. So there's Peter's website, and there's the code that produced it. There's Peter's PR. There's me and Sanket's code, and there's one of our old. Oops, I didn't mean to click there. Command. I got it. Okay, we have a policy to Miniscript compiler. Let me see if this is working now. Oh, nice. It was something was broken a couple hours ago, but it's fixed. So here's up top. Here's a policy in the high-level language. I click compile there, and then you can see it output the Miniscript. As you can see, the Miniscript and the policy look the same, except the Miniscript has tags on the ands and ors, and it has these extra wrappers stuck in there. It also gives you a bit of information about the script spending cost. You can see, like, I put this 9 here saying, like, this branch of the OR is 9 times as likely as the other one to be taken, and it gave me some, like, average expected weights for spending it. It also wrote out the script here, which is kind of cool. So this is Bitcoin script, this Miniscript. Those are exactly equivalent. Straightforward, linear time, translate between these. It's literally a parsing thing. It's not even it's a parser that you can write with 1 token look ahead. I should be clear, so it is actually linear time. If you have a Miniscript, You can run it through this analysis tool. It gives you some cool stuff. And then here is the Miniscript reference that I mentioned. So here are all the different Miniscript fragments and the Bitcoin script that they correspond to. Okay. Here's the type system I mentioned. You have these 4 base types, B, V, K, W. This is what they mean. The 5 ones, this is what they mean. Here are how they propagate forward. You can see all of the kind of leaf fragments here, like pub key checks and time locks and stuff, just have certain properties, like the NDU here, ONDU here. If you have combinators, like and ors and stuff, then the properties of those kind of propagate from the properties of the children. Okay. You can convince yourself that all of these rules are correct. There are a lot of them, but you can just go through them if you really want to not trust and verify. You can check that these are what you expect, and then they're very straightforward to implement. James actually wrote all of this, and then Sankit looked over it in Python for the Bitcoin Core test, the Python test framework.
And I just use this website.
Yeah, actually, yeah, and you can just copy the stuff right off the website. It's really nice how this turned out. Like you guys should have seen some of the earlier versions of this website. There's some banter about the resource limitations, which matter if you're writing a compiler, but otherwise don't matter. Some discussion about security. Then here's the second part of the. Oh no, this is about how to satisfy and dissatisfy things. The different ors and ands have different ways of being satisfied or dissatisfied, and this is where the different trade-offs in terms of weights come from. There's a discussion about malleability. Here's an overview of the algorithm that I described. Here, this is more talk about malleability. This is a non-malleable satisfaction algorithm that I mentioned. You can see it's a little bit more technical than I said, but it's actually not a lot. I think Peter overcomplicated this. Well, he didn't. Every time I complained about stuff, he had some reason that he had written stuff the way he did, but
he's very precise.
He is very precise, yes. And then here are the 3 properties for non-malleability. And then here's how they propagate. You see it's basically the same as the last table. And there you go. This is a Miniscript. All the Miniscript is on this website with basically the entire contents of this talk and justification for everything and the detailed rules for doing type checking and malleability checking and for producing non-malleable optimal signatures. It's all just here on this page. It's a lot of data, but you can see, like, I can scroll through it in a couple seconds. It's actually not like, compare the reference book for any programming language out there to this web page that's like 3 pages long, right? I mean, it actually very small and straightforward, and ordinary people can get through this and convince themselves that all the design decisions make sense, which I think is a really cool, this gets us to the point where we really can laugh at the Ethereum people for having a broken script system. And until now, we couldn't. It really was just like Bitcoin script pointlessly had all of the problems of Ethereum and more. But here we are. So here we're living the dream. When will this get a bit number? It's a good question. Do you think it should have? I guess it should have a bit number, right? I mean, a lot of things do that aren't really consensus. BIP32 has a number, right? 49 does. PSBT has a number. I think our thought was when we solve these open problems, right? Which we keep thinking are easier than they turn out to be. That's a good question. I don't have a plan for asking for a number. My feeling is that I want to finish the Rust implementation, and I want to have something better to say than this is open regarding the optimal fee estimation. And I'd like to have a finalizer that somebody out there is using. And then I would think maybe if Miniscript should have its own number and the finalizer should have its own number or something like that. I don't know, but I don't have specific plans for asking for numbers. But I agree, I think it should have a number. It feels like the kind of thing that should.
It feels like there should at least be some other documentation than Peter's website.
Yeah, I mean that's
that may or may not randomly disappear.
Yeah, no, that's fair. And right now the other documentation is the implementations, and you're right. There should be something in a real canonical repo, right? And the BIP repo is a good candidate for that.
So now that you've gone through all this pain, are you going to come up with a new TypeScript version that, because I guess it's version, right, TypeScript?
Yep.
So you come up with a new one that has only the opcodes that make life good and maybe completely different opcodes? Or?
Yeah, so the question is whether we are going to optimize TypeScript for Miniscript. And the short answer is actually no. So when we start to do this, we wind up getting rat-holed pretty quickly. So there are a lot of aspects of Miniscript that are kind of specific to the design. Oops, to the design. Wow, what a lot of things. To the design of Bitcoin script. You can see like how many different fragments we have here. And so if we were to create a new script system that directly, like efficiently implemented the Miniscript semantics, we would actually want to make a lot of changes, and it would result in a simpler and different Miniscript that we haven't designed. So what we landed on was just getting rid of check multisig, because that was a particularly egregious thing, and we made no other changes, because there wasn't any clear shelling point or point where we could stop.
Did you get rid of -0?
We didn't even get rid of -0, no. Yeah, that's an interesting, I mean,
And the infinite length malleable 0?
yeah, no, so we might have made minimal if a consensus rule.
Yes, I think.
Yeah, I think we did. So yeah, so that I think actually covers the issue with this giant booleans. Any more questions? We got still a few minutes. Michael?
So what should be in core and what shouldn't be in core? So there's 2 PRs currently open, like Peter's, James's for the test framework. I'm assuming there's going to be more functionality in your Rust library than will get into core.
Yeah.
Like,
Yeah.
how much?
The question is what should be in core and what shouldn't be in core. So core should have the ability to sign for Miniscripts. Well, that's not really a lot to signing. You actually don't need to understand the script to sign it. But core should have the ability, I think, to recognize Miniscripts that it has control over.
Core should be able to finalize.
And core should be, okay, so that you could go either way, but I also think core should be able to finalize, as Andrew says. So that means that that you have an RPC or something where you give it a PSBT with all the relevant data, and core will be able to output a complete transaction. And you could argue that that's kind of like a separate thing than what core's primary job is, but it's also a really fundamental thing to creating transactions. And if we're going to have like the create raw transaction, sign raw transaction API, a very natural successor to that would be a general PSBT finalizer, right? That is.
So part of it is that there's a plan to have the core wallet store Miniscripts, which that directly implies core has to be able to finalize those.
Nice. So
And
what?
sign them.
So Andrew's saying like actually there's plans for core to support Miniscript in its descriptor, in the descriptor wallet, to have arbitrary Miniscripts. And then that would require it be able to finalize just in order to sign for its own outputs. So maybe that's a good question. What should not be in core? So there's a compiler here. That should not be in core. That's like a separate kind of beast of a thing doesn't even have like necessarily a canonical design. There are some like interesting fee estimation and analysis tooling that I've been hinting at. Those probably don't belong in core. Those probably belong in their own library or their own RPC tool or something like that. Because they're only relevant to weird
We should get out the fee estimation out of core.
Pardon?
I mean, the fee estimation should be its own process or its own interface.
It's hard. I mean, core should be able to estimate
Core
fees
needs
for
to
its own
estimate
stuff.
fees, so
Right, but in core, should you be able to say like these keys are available and these ones are not, and these ones are trusted and these are not, and like so on and so forth? I mean, you can get into really complicated hypothetical scenarios that Miniscript can answer for, but I don't think it's core's job to answer that. And I think Peter would agree, because Peter continues to disagree that my scenarios are even sensible. So.
When you were like giving up this original plan of making Miniscript like a preprocessor of script, was there a certain detail that was convincing you, or was it just the sum of all the complications?
Yeah, it was. That's a good question. The question is when I had to give up my original dream of Miniscript and the policy language being the same. I think it was Peter just like explaining the way that he had separated the policy language from Miniscript in his head, because I didn't have that separation in my model of things, and he explained conceptually that first of all the policy language had this this information about branch probabilities that could not be expressed in script. There was just no way I could preserve that in going to Bitcoin script. And I think that was what did it. And then I realized that there was no way I was going to be able to unify these things. And his point about, and he had another point, which was that once you were in Miniscript, everything is deterministic. Like Miniscript has a deterministic transformation to script and back. But the compilation step from the policy language to Miniscript, that involves like doing all sorts of optimizations, and there is a lot of potential there to like discover new optimizations or give more useful advice or something. And that's kind of a part that shouldn't be a component of any protocols, or at least if you had a compiler that was part of some protocol, it would need to be constrained in some way that we didn't want to constrain that early on. So we had this clear separation both between the policy language having extra data that we couldn't preserve, and also the policy language being a target for a lot of design iteration on optimization kind of stuff. And then we could leave Miniscript alone as a pure thing that was like a re-encoding of Bitcoin script, and for which all of the manipulation we wanted to do clearly had deterministic results. So I could have like my beautiful little Miniscript world where everything was deterministic and there was only one thing. And basically I could treat the policy language as just not existing. It's just some ugly thing that I need to use to get Miniscripts sometimes. And that difference in opinion between Peter and I persists to this day, where when we're developing stuff, like he puts all of his time into the compiler and I put no time into my compiler. And eventually, like Sankit rewrote the entire compiler for the Rust implementation because mine didn't even work by the time we were done changing the language. Yeah, and basically once Peter described that separation, I was willing to, I realized that this was actually a sensible separation and that was something that we should move forward with. And that my dream of a simple Miniscript could still be preserved.
Would the policy language be supported in core? Probably not.
Yeah, so the question is will the policy language be supported in core? And Andrew says probably not. I think that's probably true. I don't know. I mean, that would be up to Peter. If Peter were here, he could give you some answer. I think it comes down to Peter's opinion. I guess Peter needs at least one other opinion to get submerged, but I mean, my guess would be no. The compiler is a pretty complicated piece of software that's doing this kind of one-shot task of figuring out an optimal script that doesn't really integrate with descriptors, obviously, in a natural way. And that has some more design iteration that we want to do. So I have questions like if you have like a threshold of like 3 of 5 things, maybe you can get a more optimal script by reordering the components of the threshold. That's something that's not implemented and probably is intractable in general, so we have to devise some heuristics for example. There's design iteration on stuff like that still needs to be done. My thinking of it is just not.
It may also just get stuck in review from everyone not understanding.
Right, yeah, and Andrew said it might get stuck in review, which I certainly believe. Like on the Rust side, I haven't looked at Peter's compiler, but on the Rust side, the compiler is like literally half of the entire library is a compiler. It's much more complex. Everything else is really straight. It's like all the same algorithm. It's like iterate over everything, recurse in these specific ways, and you can review it in a modular way. The compiler is this like incredible, like propagating information upward and downward, and like going through like different things and like caching different values and ordering them in certain weird ways, and reasoning about malleability at the same time. And it's quite a beast to review. Yeah, I can't see it getting through the core review process just because it is such a complicated thing.
Any other questions? Yeah.
I was going to ask a really, really high-level question. So Craig Wright, you mentioned earlier, he wants to apparently secure about 6,000 patents on blockchain technology, which would obviously affect Bitcoin and the Ethereum communities and every other blockchain. When do you think he's going to jail?
So, Craig Wright, as I understand it, is a UK citizen.
Do you want me to stop the camera?
No, I mean, I don't. UK law is different from US law and different from Canadian laws in ways that kind of benefit him. So, for example, I understand in the UK that the truth is not a defense to a defamation suit, for example. So one thing that Craig, so ignoring all of the perjury and so forth, right? He came to some US court and then he got in a whole bunch of trouble for contempt of court for throwing papers around and crying and so forth. But independent of that, and independent of the patent trolling, which unfortunately I don't think violates any laws and I think he can just do, the other legal thing that he's in the middle of are these defamation suits and these counter-defamation suits and stuff like that. And I'm not a lawyer, of course, but my understanding is that because he's doing most of this crap in the UK, UK law is a bit more favorable to this kind of trolling than it is in other jurisdictions. And like in the US, he probably wouldn't have gotten any, like, had no ability to do a lot of the stuff he's doing.
Some cases have already been dismissed here in the UK. They don't have jurisdiction over those kind of things.
Okay, cool. That's I'm hearing that some cases have been dismissed. So, yeah, I know your question was a joke, but it's a good question. I don't know. I wish he would go to jail. Yeah. If wishes or fishes or however that goes.
Yes, if we have like Opcat to force like nonce reuse to do this kind of protocol, could you catch up this with Miniscript or do Miniscript extension?
Yep. Yeah, so the question is, what if we added opcap to script? There are a bunch of benefits, like forcing nonce reuse and like doing other things. The short answer is yes, we would extend Miniscript to support the new capabilities of opcap. But what specifically, I don't know. We haven't really thought through how we would want to do that. But the way it would look is we just add more fragments to this website, basically. But yeah, it would have to be things that were composable. Yeah, I don't know. I don't have specific plans. But definitely, I'm sure there will be some things that you can do with opcat that we will just add to Miniscript.
Any other questions? Yeah.
You basically reduce the use of script with Miniscript to pre-images and keys. There's also all things you can do with script, right?
Yep. Well, so with script you cannot do time locks.
My question was coming after this. For how long do you see Miniscript being used up until we basically only use script?
So scripts are interactive and require online keys. So I think that Miniscript will forever be used for cold storage. That's my feeling, is that we're going to tend towards a world where cold storage keys use Miniscript as a means of having complicated redemption and recovery policies. And the rest of the world doing like cool, like fast-paced interactive things would move to scriptless scripts. But I also think there will be a long period of research before people are comfortable deploying scriptless scripts in practice. Because they are like complicated interactive crypto protocols, right?
We may have hardware wallets to do also like hardware wallet support with the same assumptions in the code wallet, not a deep code wallet, but just a code wallet. We may have this kind of stuff already too. So.
Okay, yeah. Yeah, the Lightning developer says that we might have hardware wallet with support for, well, I'm not quite sure what you're saying, just with support for Lightning?
Yeah, support for Lightning and this kind of scriptless script.
Oh, and also scriptless scripts, yeah. And so yeah, so when we get to that point, I imagine people would just transition to scriptless scripts for hot stuff. Yeah, I don't know how quickly. It seems to me that we've got a little while, at least probably another year or two, maybe 5. In seriousness, like these are complicated interactive protocols. But in the far future, I think Miniscript is for cold storage, and scriptless script is for hot stuff.
So a question.
We're past 8:30, just so Michael knows. But
what would simplicity be for then, like this new sort of language that's being developed?
Oh, cool. So that's not a question I can answer in 30 seconds. But the question is what is simplicity for?
Miniscript and script.
So Miniscript can only do time locks, hash locks, signature checks. Simplicity can do anything with the same kind of assurances. Because simplicity does significantly more stuff, the kind of analysis that you can do is much more powerful because it's defined in the Koch theorem proving system, but also much more difficult. So if you have a policy that you can encode just in Miniscript, you probably want to use Miniscript. In simplicity, you can implement all of the Miniscript combinators. So you can just compile Miniscript, or you can compile Miniscript policies directly to simplicity, which is kind of a nice thing. But the short answer is simplicity lets you do all sorts of stuff that you cannot do with Miniscript. It will let you do covenants. It will let you like interact with confidential transactions by like opening up Peterson equipments and stuff like this. It will let you create like algorithm that you can create like limit orders and stuff and like put those on a blockchain and have like coins that can only be spent if they're being transferred into a different asset under certain terms. You can do vaults where you have coins that can only be moved to a staging area where they can only move back or have to sit for a day. All these things that the Miniscript, a lot of what I just said Miniscript will never be able to do because they don't fit into this model of being a tree of spending conditions. So simplicity is just infinitely powerful. I mean, you can verify any the execution of any Turing complete program in simplicity.
Cool. Okay.
I think we've got to wrap up.
Andrew.